Okay. No, I'll use the other one there. All right, I guess we'll get started on the last talk of the day. And I'm going to take things in a little bit of a different direction, but if you stick with me, I promise it'll come back to QIS in the end. But I'm covering millimeter wave and terahertz R&D that's happening up at SLAC. It's not everything that's happening at SLAC, of course. But I'd like to start by giving a little bit of an introduction to what SLAC is and what we do in RF accelerator research. And then I'm going to talk to you about terahertz, and I'll use millimeter wave and terahertz as synonyms today. And in particular, what we're doing in terms of terahertz R&D and trying to generate ultrafast beams, which is a very important part of SLAC's mission. And then I'm going to go on and start to talk about kind of the slew of millimeter wave devices that we are working on for QIS applications. And you heard about a lot of this work already through kind of some of the collaborations that are going on. And then I'll touch back onto the topic that is before this. And then finally, time permitting, I wanted to talk a little bit about an idea that's been rattling around in our group for a while, which is looking at electron beam-based sources for making millimeter wave entangled photons. And I'd like to see if that could stimulate some discussion today here at the workshop. So SLAC is a DOE national lab in the Office of Science. It is managed by Stanford and part of the university. And we're just located a couple of miles up the hill. And started in '62 with a mission that was focused purely on particle physics. And we built this 2-mile accelerator, which was used for a whole slew of different experiments over the years and played a central role in particular in discovering quarks. And since then, the mission of SLAC has diversified. So now it's a multi-office lab, and in particular, it does a lot of work in terms of basic energy sciences, but it still has a very active high energy physics program. So our group is actually within the RF Accelerator Research Division at SLAC. So we have a very closely connected mission to what is still going on at the lab, because there are still a large number of accelerators that are operating at SLAC, and trying to develop that technology further is a big part of what we need to push the science mission forward. We also do a lot of work with external groups. So we do everything from designing, building, testing, and using these types of accelerators. We have our in-house simulation tools. So we have a code that's called ACE3P that does everything from ENM to thermomechanics to beam dynamics, and even radiation. And we work, I would say, primarily in S through X band, so kind of 1 to 10 gigahertz range. Although we have a strong program that goes all the way up to terahertz, and a few unique experiments that are down in the VLF range. So just kind of some examples to give you a feeling for what the, let's say, majority of what we do is. These are high voltage test stands where we can test high power RF sources, high power RF components. We've designed entire accelerator facilities for example, one at RPI that's being built. We do a lot of innovative technology development for accelerators themselves, and then that's that simulation code I was mentioning. Kind of more on the research side, a couple of examples here. So the first one on your left is a collaboration that we have with Arizona State University, where they're trying to build a compact, coherent X-ray light source that's based off of a technique which involves pre-modulating the electron beam through diffraction. And we were very involved in both the developing the theory for that, as well as doing some of the first experiments for this beam patterning technique at SLAC. And now that facility is being built, and our group is actually still involved and is doing the RF deflector, which is the most sensitive RF component in the entire accelerator. Then we do things at extremely high peak power. I always like talking to QIS people because we have very definitions of high and low power. So here's an example of a project where we're going to use 300 megawatt peak power RF pulses to try and get an RF photo injector to extremely high gradients. And this is a way of getting a very, very tight phase space for the electron beam that is produced. So if I ever say low power or high power, you have to just kind of double check what scale I'm on for the moment. And then finally, over here on the right, we also do kind of trying to push the limits in terms of high gradient acceleration, things for future colliders. So this is something we're working on, which is going to test these cryogenic accelerators that we were just talking about a minute ago. Okay, so I'll start today's talk by kind of highlighting a series of experiments that we did in the terahertz frequency range, trying to generate some ultra-fast electron beams for diffraction. And this was really a collaboration between our group and the UED team, ultra-fast electron diffraction team at SLAC. So if you look at SLAC right now, in terms of its accelerator facilities, what's really driving scientific discovery there is how short of an X-ray pulse or how short of an electron bunch can be produced. And that doesn't really change with scale. On the left here is LCLS, which produces these very short X-ray pulses, and on the right is the UED facility, which produces these very short electron bunches. And our question is kind of how hard can we push this in terms of temporal resolution so we can drive these experiments that look at the dynamics of matter. And kind of the fun thing for me is to point out that actually the RF technology, the accelerator technology that's driving both of these facilities, even though one is less than a meter in length and the other is a kilometer, is actually the same. So these have the same RF photo injector for them. So why do we want to get to shorter and shorter timescales? Well, it's just great for capturing the dynamics of motion. So the figure on the top right, it's actually, I would say, the first example of this art, and was actually done here at Stanford. So Leland Stanford settled a long-standing debate about whether or not a horse has all four of its hoofs off the ground when its feet are under it or stretched out. And they commissioned the first kind of flash photography that was able to conclusively show that it's actually when the hoofs of the horse are under. And so if you look at paintings from like the 1800s, they'll often show that the horse has its feet all off the ground when they're spread out, but that's actually not correct. And it's just really hard for your eye to see it. So, this kind of stroboscopic technique was developed here at Stanford, and we're continuing it, well beyond the timescale of electronics, but actually onto the timescale of molecular motion. And ultimately, we're trying to get down to the electronic timescale. So something that's in the range of 1 femtosecond or below. It would be really, really interesting for both these types of X-ray and electron sources. So how do we do that? Well, if you look at RF technology that's really out in the field, most of it has an accelerating gradient that's around 30 megavolts per meter. And really this plays a lot into the limits of what you can do in terms of beam manipulation, because it kind of sets how strongly you can force the electron bunch to compress. And so we'd like to do something where we can get it up much higher in accelerating gradient. So stronger fields, we can put more pressure on the particles as we're accelerating them and keep them together. But that also requires really a different type of RF source for powering these types of accelerators. So most accelerators that are out there today are powered by things like klystrons or magnetrons. They require these high voltage modulators, et cetera. And really, we'd like to move, if we go into this frequency range, into things like sources that are based on lasers, lithium niobate, converted into the terahertz range. And I'll show you a little bit more about that here in the slides. So what makes ultra-fast electron diffraction a great kind of first step for being able to do that? Well, what you're doing in UED is that you are trying to make a very short electron bunch, send that in with very high precision in terms of relative timing to a pump laser. The laser pumps your sample, the electron bunch goes through the sample either at the same time as the laser or slightly after it. And how the diffraction pattern changes actually tells you how the atomic structure of the material changes. And so your temporal resolution is really just limited by the variation in time of arrival for this electron bunch, so how much jitter it has, as well as how long this electron bunch is. So ideally, we would like to get this onto the 100 femtosecond timescale or better. And what you'll see is that, that this turns out to be quite challenging with today's technology. And ultimately, we do want to get it down into the femtosecond timescale. And I'll show you how you can do that using a timing tool, for example, like a terahertz transverse deflector. So, as I said, why would this be good use case for a terahertz accelerator? Well, you already have a laser system. And so if you do your terahertz generation with the laser system, it's fully synchronized. You don't have to worry about that aspect of it. And it turns out to be a huge advantage. So you can both manipulate the electron bunch as well as get rid of this jitter problem. So the technique that we like to use a lot at the lab is optical rectification. And in particular, the style called tilted pulse front. So what you do is you have a relatively high power 800 nanometer laser pulse comes in off a diffraction grating that tilts the phase front of the 800 nanometer that gets then focused down into your lithium niobate. The tilt in the phase front gives you phase matching between the 800 nanometer and the terahertz that's generated, so you don't have to do anything like polling. And then the terahertz pulse gets generated basically from difference frequency generation. And the terahertz comes out perpendicular to the space here on the side. The typical waveform that you get looks like this, and it's a single cycle. So something that has a lot of bandwidth and a very, very wide spectral amplitude. So how can we use this to manipulate an electron beam? Well, most traditional accelerators are used with very, very narrow band sources. And so we had to do some development in terms of the types of structures that we could use. So here you're actually seeing two different types of devices. Both of them are effectively parallel plate waveguides. Great thing about a parallel plate waveguide is it doesn't have dispersion for the fundamental mode. So you don't get any spreading out of the single cycle pulse. And then you can just tune the overlap between the field and the electron beam by setting the gap size correctly. So in this configuration here, where the electric field is in the longitudinal direction, we can put a chirp in terms of energy onto the electron bunch. And through differences in velocity, we can get compression as it propagates. It actually compresses so much that we don't have a way of measuring it at UED in terms of what its bunch length is. So we have to use something that's called a transverse deflector. And again, we have to use a terahertz pulse to do this. So this time the electric field is oriented perpendicular to the electron beam, and you give it a transverse momentum. And that gets the beam to spread out. So when the video runs, you'll actually see that it stretches, and how long it stretches tells you how long the electron bunch is. So the smaller it would be, the shorter the electron bunch duration. So you have to synchronize those and overlap them. And then here you can see that the full measurement of the bunch length happens there. So it changes where you are in the overlap of the terahertz cycle, and you have to calibrate it by the minimum and maximum and how much transverse deflection you're getting. But you can get a really, really good measurement of time of arrival. So actually, each one of those pixels is seeing about a third of a femtosecond in time. So if you do this after the electron bunch has gone through the diffraction pattern and you streak the diffraction pattern, you can get timing information from the scattered light that's sub-femtosecond. And we've actually shown that in some experiments more recently. But anyway, so yeah, that's what we have going on. We have this terahertz-driven compressor here. You can see again, it's a parallel plate waveguide. The beam is compressed down by this nice horn. You'll actually see something that looks quite similar to it later on inside of a waveguide. And then the transverse deflector over here is just effectively a gap in a foil. Okay, and that's what the thing looks like in real life. You can't tell, but there's a hole that's on the top for the electron beam to pass through. And it has to be very, very sub-wavelength. Otherwise, the field leaks out into the beam pipe, and it causes a lot of problems. So this is what the actual kind of layout of the experiment looks like. So you have an RF photo injector. You have a single laser that drives the entire process. So high power RF comes in and establishes a field which accelerates the electrons initially. the electrons are emitted off a copper photocathode surface in this cavity from the UV pulse that's upconverted from the 800 nanometer. And then you send the 800 nanometer down, you split it into two, and you have two independent terahertz sources. They both produce single cycle terahertz pulse. The first one is used for compression. That drifts about a meter. The second stage here is for transverse deflection. And then you go on a few more meters to the location of the detector. Okay, and with that, we were able to show that you do, in fact, get compression. So a reduction in bunch length by about a factor of 3, so 105 femtoseconds RMS down to about 40. And then the other thing that you get is you get reduction in jitter. So if the electron bunch, its mean arrival time is late, the mean energy of the electron bunch goes up, so it comes in a little bit faster. If it arrives early, the mean energy goes down, so it takes a little bit longer to get to your sample. So both your timing resolution and your jitter improve, which is really, really nice in terms of the experiment. But of course, what matters is, do you still get a good diffraction pattern out of a sample? And here you can see an uncompressed example on the right and a compressed example on the left. Sorry, I got that wrong. Left for uncompressed, right for compressed. And this is in polycrystalline bismuth. And then here we're actually doing an experiment where we're pumping it with, again, 800 nanometer light. This is just the By-Waller heating, so it's just how long it takes for heat to propagate in the system. And what you'll see is that, you know, if you try to measure the characteristic timescale of this, the uncompressed case gives you something like 280 femtoseconds, but you get a significantly shorter measurement with the compressed electron bunch. So if you had done this with the uncompressed case, you would have actually come out with the wrong answer. So that was really nice to see. And there's been, you know, kind of a number of follow-on experiments that have used this type of setup for characterizing the beam, for looking at how samples behave, and for doing you know, different types of beam manipulation. For example, as the terahertz is overlapped with the actual sample itself. So it's been a nice addition to the UED facility. Okay, so now I'm going to jump, and then I'll jump back. But you know, through kind of our interest in millimeter wave and terahertz devices, years ago we started collaborating actually with the MIRS group in particular, and that's expanded to several other groups on campus. So there's a lot of students and postdocs who've contributed to the work that I'll show in the next few pages. But what I'd like to do is give you a feeling for the kind of variety of QIS devices that are needed and that are in development in this area. So I think some of this was kind of already covered earlier today, but you know, in general, if we want to, you know, connect any kind of superconducting or optical system, we're interested in being able to do quantum transduction, convert the frequency of these photons up or down. And then there could be other advantages. For example, if we can convert the frequency up, we can have connections between fridges that are at warmer temperatures instead of needing to do cryogenic connection between fridges, et cetera. So what is kind of some, you know, techniques that we could use to do that? Well, the one in particular that we've been collaborating with is trying to do this over two steps. First, trying to do this with a superconducting transducer that would go from microwave to millimeter waves, and then eventually take that millimeter wave signal and do transduction from there up into the optical range. The idea being that as you go higher in frequency again, you can work at progressively warmer stages, in particular for the actual links themselves, and deal with some of these issues again that we heard throughout the day. For example, how many connections can we have into the fridge? If it's at low frequency, it's a lot easier, for example, if we can consider the bandwidth of a fiber system. So that's not to say that by any means this is the only approach. A lot of different groups are out there and are looking at competing approaches for transduction. And again, a lot of them touch also on doing an intermediate step in the millimeter wave range. So definitely an active area of research as we heard today. So I'll just talk a little bit about the microwave to millimeter wave transduction part of this. So the idea here, again, is based off of the kinetic inductance in the superconducting material, and then doing full wave mixing, where we take a single low frequency photon at the microwave frequency, combine it with two at the intermediate pump frequency, and then get out our signal at the millimeter wave range. And really for the purpose of today's talk is to think a little bit about, well, what are the different types of devices that need to be generated for this? So here you can kind of see a zoom in of not only what the interconnects look like, so we have millimeter wave rectangular waveguides that have to get to the chip, but we also have to have low frequency signals that couple in. And then zooming in on the chip itself, you have here kind of located the highest frequency resonator, something that would be around 100 gigahertz. Your intermediate frequency, which would be for your pump, something around 50 gigahertz. Your resonator for the microwave line, which is, of course, in the few gigahertz range, and then the readout that follows from that. So where the project started was really kind of looking at the behavior of these millimeter wave resonators. And at first, that looks like a relatively kind of simple device to fab, but of course, getting the frequency for it correct is not so trivial. But we were able to see resonances, kind of this dipole antenna configuration that were in the 100 gigahertz range, and also do kind of some of the first feed-throughs with rectangular waveguides or horns that pass through windows, and actually do some measurements of this device. So some nice results, just kind of seeing that, yes, in fact, we can get a resonance that's in this frequency range. Quality factor is pretty close to what we expected, and then kind of reasonable behavior as you cool it down. But this, of course, kind of leaves out all of the other stuff, being able to do multiple millimeter wave resonators in a chip, reading out the signal, connecting it up to a microwave resonator, et cetera. And so the focus more recently has been on trying to do that part of the device. And this is some recent work by Farhan and in collaboration with others, of course, really looking at how we can do the connection for the microwave feed here in the device. And so here, what you can see is the chip that would have the millimeter wave structure on it. You can see, again, the coupling onto the chip happens through a very similar horn to what I showed you earlier in the presentation. Kind of what I want to focus on here is that in order to get the microwave signal in, you have to do a perturbation. You have to make sure that that has a cutoff frequency that's high enough for you not to get coupling. You have your substrate. You have to make sure the substrate doesn't couple to millimeter wave mode, so you can have these vias there. And then you have this very tight environment where you have to do a wire bond that actually bridges from the chip inside of your millimeter wave waveguide out onto the PCB. And even if you do all this, you still do get quite a bit of resonances or parasitic modes that actually show up. And in particular, what we'd like to see is an S21 that's really flat in this case. Instead, we have some resonance showing up. So things can get even a little bit more complicated. You can start to think about putting filters on the microwave line itself. And this way you get a signal that passes through in the microwave range, but then you can reject any millimeter wave signals that might make it out on what effectively now looks like a little coaxial waveguide here, because there is a conductor in the middle, and so you don't have a cutoff frequency, strictly speaking, for the fundamental mode. And what you can see is, all right, great. You do that, you're able to get really, really good transmission through there. And so you think you have a good approach for it. So it is possible to do all of these connections, but definitely very, very challenging. So the kind of other thing that I want to talk a little bit about is, then also being able to do the characterization of these materials. So every time we do the deposition, change place, there can be differences in terms of the material properties themselves, differences in terms of the quality of the fabrication that's capable. So this is some work by Charlotte trying to kind of speed up that step of the process. Here again, this looks actually very similar to the type of features that we saw in the JPL presentation, where you have waveguides that come in, and then you have little antennas that stick out into the waveguide structure and couple onto a microstrip line. And what you can see here is that when you have the feed through present, kind of in this transmission configuration, you get a nice bump in signal here, indicating that you're getting some strong coupling onto the coplanar waveguide. And then just showing some photographs of what this looks like in the device. Then what's nice with this is it's relatively easy to have, again, sort of this issue of calibration locally figured out, because you can do different types of transmission line setups. You can do through transmission, you can put a resonator on there, you can do a short, you could try to imagine how to do a load there. And that could start to, again, sort of speed up how you do your calibrated measurement of material properties and what you would expect from that device. Still, you have your, again, another setup that you need to make for doing these types of characterizations. So this kind of gets me to my point, which is that, of course, there's a lot of challenges with millimeter wave devices. I certainly think that S parameter measurements will remain the gold standard for characterization. Like, you're never going to get around that. But in order to do proper characterization, this really requires very careful packaging, strong simulations. You have to think about parasitic modes. You have to confirm what mode you're actually seeing, figure out the losses, calibrations, et cetera. Make sure that the device frequency is aligned with the instrumentation that you have, et cetera. So again, it's a complicated landscape to work in. And so I think one of the challenges is, can we develop more characterization techniques that could speed up this development, that would allow you to do mode identification, that would really do quantitative measurements of coupling, for example, between devices by measuring the actual field distributions on them, and things that could be hyperspectral, so have really, really wide bandwidth in terms of characterization. Okay, so hold that thought for a little bit. So now I'll jump back to the beginning of the talk. And again, as I mentioned, we did this experiment. We have these terahertz sources. We do generation. We've even done experiments where we have symmetric feeds for getting better balancing of the fields in the compressor, et cetera. And so after thinking about this, we said, well, this is quite complicated. Why don't we actually try and bring the terahertz generation into the vacuum chamber so that we can directly manipulate the electron beam? But if you do this, you have a challenge, which is you have to be able to control the phase front, because otherwise you don't have a way of properly manipulating the electrons as they go by. So what does the electric field look like as a function of time? And how do I make sure that the phase front itself is propagating with the speed of light as the particles go by? So we needed a way to be able to tune the source itself and provide, again, that proper phase front as the beam goes through. So there are some very good techniques for being able to measure the electric field as a function of time and its phase. And that's using electro-optic sampling. I already showed you that earlier in the presentation with the measurement of the single cycle terahertz pulse. And the idea behind it is relatively simple. Use something like a gallium phosphide crystal. You send a terahertz pulse onto it. The amplitude of the terahertz field changes the index of refraction for an 800 nanometer pulse, and then you measure how that polarization is rotated as the 800 nanometer pulse goes through as a function of time. And the way that this is typically is done is generate your terahertz pulse, you have an off-axis parabolic mirror, you transport it, you focus it back down, and then you do this collinear measurement of it. And you just overlap your terahertz spot with your 800 nanometer. And then you send your 800 nanometer to a single pixel detector like a photodiode, and you get your measurement. The problem with that is, A, it's not actually where your source is. and B, you don't really get any resolution in terms of spatially what the fields look like. So the idea was, can we come up with a way to actually bring this into the near field of the antenna, the near field of the source itself. So we bring the gap crystal in to actually be in close proximity to the emission surface of the lithium niobate. And we started doing those experiments by rastering very slowly the 800 nanometer beam over the spot, and that works really well, but it's extremely slow if you want to have good resolution for it. So then the idea was, well, let's actually image that onto CCD instead of doing this rastering, and then we can get high spatial resolution of the entire terahertz field as it's moving out. And then the temporal resolution is very easy because you just change the delay here. And if you have an accurate stage, you can do 10 femtosecond steps, no problem. So this just kind of shows some views of what it looks like. This is the lithium niobate. The pump comes in here. That's the gap crystal. The probe beam comes in. You have a highly reflective coating on the backside. So the probe beam bounces back out and the terahertz passes through with it. So this are what some kind of single images look like on the CCD. You can get really, really nice excuse me, resolution in terms of what you're actually seeing on the crystals. So something that's very, very sub-wavelength on the order of 10 microns per pixel. This is what it looks like when the terahertz signal is on. This is what it looks like when the terahertz signal is off, and the difference between those two. So this is again, just kind of a one snapshot in time of what that terahertz field looks like. So now I'll actually show you a movie in time, little, very, very small step sizes, 10 femtoseconds. And there we go. What you'll see is that the terahertz pulse is actually translating vertically as a function of time. So it's translating vertically as it comes out of the lithium niobate. You can see it absolutely clearly. You can get really good measurement of what the fringe fields look like. Like this image is slightly saturated, so you can kind of see what those look like, etc. You can also see that it's highly monopolar in this case. So it's predominantly negative, like there isn't a strong inversion of the field. This was like a fully optimized source for optical rectification. We work very closely with Matthias Hoffmann, who was one of the originators of this technique and has been doing this for like 2 decades now, and is, like every terahertz pump probe experiment that's done at SLAC he's involved with. So like, the pros are involved here. This is absolutely not what anyone expected to be coming out. Like this should not be moving vertically. There's really kind of no explanation for it. It's monopolar. If you go into the far field of measurement, it's bipolar. Like, so turns out that actually, like, we really had no idea what we were getting out of the source. And it took a long time to kind of trace this back to what the problem was, but there were some cylindrical lenses in the setup. And it turns out that aligning those cylindrical lenses is like next to impossible without distorting the tilted pulse front. And so again, we were able to use this to image what was going on with the field and change it. And now if I showed you the optimal case, it roughly has the same conversion efficiency, but it gives you what you would expect to come out of an optical rectification source, which is a flat phase front, which is bipolar. And if we intentionally change the alignment of the optics, we can then control that phase front and we can tilt it so that it propagates with the speed of light and it'll interact with the electron beam. So I think something that we should really think about and approach as a community is, well, how could we change the way that we're characterizing some of our devices? So you could basically use this exact same setup to both pump and then see what the resonant frequency is of kind of any resonant structure. So for example, let's say that you have something like this nice device that Debadri made, which you would expect to have a resonance in sort of the 100 gigahertz range. you can apply terahertz pump pulse to it. You can make it linear, circularly polarized, really whatever you need. And that'll drive an excitation in the superconductor. And then if you have this gap crystal that's close to the surface of it, after the excitation is passed, you'll have a field that's oscillating here, and that will re-radiate out into the gap. And you can actually image then both what the field distribution for it looks like. You'll actually be able to measure the time domain response of it, so you'll know exactly what the frequency of the device is. And for example, if you want to see how well it's coupled to a feed line that's nearby, you'd actually see the electromagnetic wave coupling into that transmission line. So I think this could really be useful as a tool for trying to understand, okay, I've made a batch of devices. I have devices that are at different frequencies on there, and I can use this one setup to both excite it, measure the fields, determine what the frequencies are, and think about or try to calculate, for example, what the couplings are. So this would be something fun, I think, for us to try. Okay, and then I have a few minutes left, so I want to talk about just a little bit of a different topic, which is an idea to try to find a way to use an electron beam based source for generating entangled photons. So this, I think, could be something that's interesting specifically for a set of applications that I would say is really in the category of remote sensing. And in particular, an area where right now, if you talk about doing measurements outside of a cryogenic environment, it's not really possible, except there are techniques like quantum illumination, or what's kind of more commonly called ghost imaging, that allow you to think about being able to use properties of entanglement in environments that are very, very thermally noisy. And so really this is for something that would be in the millimeter wave or terahertz range. It could be possible to do it at shorter wavelength, but it gets certainly much more complicated because what I'll suggest is that we use the electron cyclotron resonance. And for that, you need to have the electron beam in a strong magnetic field. And there, you're just using transitions between different Landau levels and multi-photon emission. So just kind of that most simple use case, which is quantum illumination. So people have shown that what you can do is kind of in the most basic experiment of taking BBO and using spontaneous parametric down conversion to make entangled photons. If you send one of those beams to the CCD, send the other one through the object that you want to image, and introduce a strong thermal background to it, you can get resolution that significantly beats the classical limit when you do this kind of cross-correlation type measurements. So the question would be, can I find a way of replacing this BBO source with something that's in the millimeter wave range and is capable of producing a large number of photons? So there are kind of different flavors of this that people have looked at, both for doing different kinds of communication schemes, as well as some types of proposed applications for remote sensing, even things like, for example, coupling an optical source with a mechanical resonator to try and do this form of generation. But I would say that nothing has really kicked off too hard in this area, so there could be some room for different types of approaches to be considered. But basically what the concept looks like is this. So if you have electrons that are in a strong magnetic field, then you get energy states which are separated by their Landau level or the electron cyclotron resonant frequency. And if the electron beam is slightly relativistic, you get this gamma factor in here, and there's non-equal spacing in between the levels. So, typically the way that people use this is by things like stimulated emission. So that's a a gyrotron oscillator uses that in a cavity, or a gyrotron amplifier uses that in a traveling wave configuration. You can get either single photon emission, where you're dropping by one level, or you can get even spontaneous emission at harmonics. It is a much rarer process, but you can also get two photon emission, both from single level transitions or two level transitions. And this would be the idea here, either to use spontaneous two photon emission or spontaneous parametric down conversion as a way of generating these entangled states. So this multi-photon emission is something that has primarily only been studied in astrophysical phenomena. So it's something that has been observed in accretion disks, for example, where you have extremely strong magnetic fields. There are also some examples that are closely related to this, I would say, in materials where you have both a photon and a phonon that is emitted. And there's some examples here for reference. So our challenge is that we have to have a resonance structure which allows you to select for a single frequency where you're going to get this down conversion to occur. Similar to the case of where you have the BBO. You don't want to have multi-photon emission over that full spectrum that's shown here. Otherwise, you get kind of two photons out at many different frequencies. And so one way you might have of doing that is you put the electron beam inside of a strong magnetic field with a cavity, and then you need two resonant modes that match the dispersion relation of the electron beam. So that to get transition, you need a photon to come out in one cavity mode and a photon to come out in the other. And the entanglement would be related to the spin of those two particles, two photons, I should say. And then the other thing that we really need to worry about in this case is being able to do this with both a high quality factor, so we can get Purcell enhancement, but also these often are in highly overmoded types of cavities. And so you need to be able to have something that would have high mode selectivity. So in the millimeter wave, something that in kind of earlier part of my career we played around a lot with was using photonic bandgap structures, because then you can be very specific about which frequencies actually are allowed to confine a high Q mode and reject modes that are at other frequencies. Now, ideally, you'd like to have something that is really high in quality factor in order to push this up. And so I thought I would kind of mention some of Tony's work and that we've been collaborating with him and Monica and others on. And recently he's been working on this superconducting quasi-optical millimeter wave cavity, and just really, I think, a very, very impressive result, being able to get quality factors up to 10 to the 9. So that would give you a huge boost in terms of the emission rate. The problem is you can't just use something like this because you need both a mode with the proper dispersion, but you also need something that'll work in a very strong magnetic field. So you might have to switch something like a high temperature superconductor. But definitely some room to think about these types of things. And I don't think it would just really be limited to paper studies, but we could also think about using existing sources at SLAC and existing magnets at SLAC in order to do some experiments. And you could even start with, for example, some single photon emission to study really if we're getting accurate measurements of emission rates, and then you could try to do it for multi-photon emission. So it'd be fun to talk to people about this if they're interested, and see if we can come up with some experiments for the future. And with that, I think my time is up, so I'll go to questions.
I have two questions. So the first one is, when you use EO sampling to measure the phase front of the terahertz, there's a distance between the crystal and the CCD, right? Do you need to compensate for the diffraction that might happen in that distance?
Great question. So okay, so the signal is encoded onto the 800 nanometer And so you're really highly collimated optical light, so you don't have to worry too much about diffraction. And the CCD is in fact quite close to, it's like 10 centimeters away.
Yeah, but if you have some small distortion on the phase front, that is a small distortion on your collimated beam, right? That small distortion would still propagate. If it would still expand, I would
guess
think.
your question is, you're assuming we come in with a flat phase front, and then it interacts in the gap crystal with the terahertz.
Yes.
And that changes the phase front.
Yeah.
I see what you're saying. I think compared to the wavelength of the light, these are like extremely small.
Okay. Okay, so you're basically not expecting any small distortion on the phase front. Okay.
I would say we don't see it because, again, it's not in the data that I showed there, but we were able to optimize it for what you would expect to be the optimal case. So it really looks like it's a uniform Gaussian that's coming outside of the terahertz. Yeah.
Another question is, when you talk about the UED, you said you have basically a pump beam and then an electron packet that is a pump probe between those two. So what does the laser beam do in that case?
The pump case?
Yeah.
Well, so it depends the material that you're studying. So for example, in what I showed, which is Debye-Waller heating, the only thing it's doing is depositing energy. And you're just seeing how long it takes for the transport of heat to happen through phonons. Okay, but it just really is very user dependent. So there's people who've looked at even things like melting in materials. So hitting with such an intense laser pulse that you look at how disorder spreads in the structure as it melts. So it just really depends on what the user wants. Thank you.
Sorry, one sec.
In your slide on the superconducting resonator, what is the mixing process that you're using? No, you had this ring resonator that you were showing.
Oh, yes.
Yep. No. Yes. This one. Yes. What is the nonlinear process that you're using in this
one? Actually, no. This one is just a resonator. We're not planning to do it. In what's shown here, there's no nonlinear effect that we would observe just as shown. It's just a resonator. Yeah. So electric field across the gap, and then current flowing around in the circle. The idea with this device was to try and make it magnetically tunable what the resonant frequency is by having these gaps in the device. And if you have a changing magnetic field, drive a current through it. Yeah.
Yeah, I was just I was just curious about so when typically at low frequencies, if you want to make an accelerator cavity, you'll do it out of metal for sure. Superconductor if you have it, but copper otherwise, right? If you wanted to try to do one of these optical accelerators, you kind of have to go to dielectric because metals are bad. In the millimeter wave, I know usually you use copper, but I'm kind of curious, like when might be there, what are the considerations between, let's say, a dielectric resonator and optical, and is at millimeter waves, might it make sense to try that, or what are the considerations?
So it really depends on the bandwidth of the source that you're working with. So if you can have something that's narrow band, metallic structures make a lot of sense if you're talking about actually making cavities. If you are talking about a source that's single cycle, we can play these games like we did with parallel plate waveguides, but the interaction length that you're limited to is very, very short. So the idea behind doing this approach, which effectively is switching to you having a dielectric, is that eventually you'd have a pattern on here, and you would have a change in the phase as the wave is coming out. So all of the energy is coming in a single cycle, but the phasing of it is different. So maybe, it just depends. Are you trying to make cavities? You would really like to have a narrowband source. If you don't have that available, you need to be a little bit more creative in terms of what you can do.
In the terahertz compression, what limits the maximum achievable compression? Can you just use a higher amplitude pulse or increase the drift length, or is there other?
So the beam has energy spread, and it can have not only a linear, but like a quadratic or a cubic correlation in energy with it, which will limit how hard you can compress the electron bunch. So being able to do much better than like a factor of 3 or 4 compression, starts to be quite hard, just because of what's coming out of the photo injector itself. That's the predominant thing that's limiting it.